Hello friends, welcome to Concepts of Geology, the Crystallography series. Today is the last class of Module 1, and on this class we will learn about the shapes and symmetries of the unit cells and mineral crystals. Okay, so this is the ultimate goal of learning. This is the optimum understanding about the Module 1, that was the distribution of atoms inside a crystal. Okay, we will learn today that what is the relationship between the shape symmetry of unit cell and the resulted mineral crystal. So let's begin. What we learned that these were the 5 basic shapes of unit cells in 2 dimensions, and with these we added one more direction and we created the 3-dimensional unit cell shapes. When the 3rd dimension was added, we created 7 basic shapes of unit cells in 3 dimensions. Okay, so that means these are the ultimate and only possible shapes of unit cells whenever we are talking about the distribution of atoms in a crystal in 3 dimensions. Fine, we are now well understood about the shapes of unit cells in 2 dimensions and 3 dimensions. Okay, but today we look into the real world of crystals. Look at this picture. This is a crystal of pyrite. What will be the crystal system or the shape of the unit cell of this crystal? Very clearly, this is a cubic crystal. Okay, the shape is very easy to identify. Coming to the next, this is the crystal of aquamarine. This is a variety of beryl. Okay, now this is having a prismatic shape, elongated in one direction, but in the cross section, if you observe, this is having a hexagonal symmetry or hexagonal shape. Okay, so from there we can say that this crystal is crystallizing in hexagonal crystal system. Okay, that means the unit cell will have a hexagonal symmetry. Coming to the next picture, this is a crystal of garnet. Okay, this is also crystallizing in cubic system. We have read it in books, but how can this crystal be a cubic? From no angle it is looking like a cube. Rather, some of my friend will say that cross section is looking like a hexagon, but we know garnet crystallizes in cubic system, so this is confusing. The next one is fluoride. This is also crystallizing on cubic system, but the shape of the crystal is not at all cubic. So that means first 2 crystals, pyrite and beryl, was all okay, but garnet and fluoride is somewhat doubtful. Now we'll try to understand how can the shape of the garnet or the fluoride is belonging to the cubic crystal system. We know the logic, as these crystals are having the symmetry elements similar as a perfect cube is having. So we will try to understand the relationship between the shape, symmetry of unit cell and the resulted mineral crystals. Now look at this cube. If I am speculating that we are having a cube and a different shape, and we are having same type of symmetry elements present in the cube and that particular shape, that means the shape which I am talking about, that should be derived from this cube. Now we will try to modify this cube without hampering its symmetry elements, and we will try to create some new objects. First, suppose I am rubbing this corner. Okay, so I will have a triangular face like this one, and with continuous rubbing the triangular face will grow in size. So I have 8 corners in a cube, and if I continue rubbing on 8 corners, we will have 8 triangular faces on each corners. Okay, so that means we will have an object with 8 triangular faces. Okay, so look at this object. This is called an octahedron. Okay, we are having 8 faces in octahedron. Octa means 8 and hedra means faces. Okay, so that means 8-faced object. All the faces are here equilateral triangles. This face is coming from this corner, this face is coming from this corner, this face is coming from this corner, and this face is coming from this corner. Okay, now next we will rub the sides of the cube. We are having 12 sides in a cube, so the resulted object which we are going to create, that will have 12 faces. Okay, look at this shape. Okay, this is called a dodecahedron. Dodeca means 12 and hedra means face, so this is a 12-faced object. This can be created from a cube by rubbing the sides of the cube. Okay, so this face is coming from rubbing of this vertical edge. This face is coming from this vertical side. Okay, these 2 faces are coming from this side and this side respectively. These 2 lower faces are coming from this side and this side. Okay, the other counterparts of the sides are hidden behind the object. So a dodecahedron is having 12 faces and can be derived from a cube. Fine. Now we will create some more objects, but not through rubbing, rather we will add some more material on the cube and we will try to create some more faces. Suppose I am adding some more materials in this triangular face of the octahedron, okay, and I am creating 3 more faces on this single face like this one. So clearly this was the original triangular face and we are creating 3 smaller triangular face in this single face. Okay, so what will be the total number of faces here? This was actually an octahedron, I mean 8 faces were there. Now we are creating 3 faces in each single face. So we will have 8 into 3 equal to 24 faces in this object. Okay, this is called a tris octahedron. Okay, tris means 3 and octa means 8. So 3 multiplied by 8 equal to 24 faces in this object and can be derived from a octahedron or from a cube in original. Now again, suppose we can increase the number of faces more here, the shape will be changed again. We can divide each and every small triangles into 2 halves. Okay, look at this object. Okay, here this was the original triangle for a octahedron. When we created tris octahedron, we created these triangles. Okay, this one, and after that we divided each triangle into 2 halves. Okay, by this line. So I am having now double faces than this tris octahedron. Okay, we had 24 faces in tris octahedron and here we will having 48 faces. This is called a hex octahedron. Okay, so hex means 6 and octa means 8, so 6 into 8 equal to 48 faces will be there in this object. Okay, so this object can be derived from a tris octahedron and the tris octahedron is derived from a original octahedron while the octahedron is coming from this cube. They are looking different apparently, but all are belonging to the family of the cube. Now we will try to find out the relationship between the symmetry of unit cells and the resulted mineral crystal. See here, this is a cube and this is an octahedron. Okay, what rotational symmetries are having in a cube? We have 4 numbers of 4-fold rotational axes in the center of each faces of a cube. Then we are having 2-fold axes on the midpoint of each and every side of a cube. Okay, and lastly we are having 4 3-fold rotational axes on the corners of the cube. They are running diagonally. Fine. And on the last we are having 9 mirror planes. Okay, so when we are creating an octahedron from a cube, very clearly observe here that no symmetry is hampered here. We are having 9 mirror planes on octahedron and we are having all the rotational axes preserved in a octahedron. We can also check the other objects. Okay, see, this is dodecahedron and this face is coming from the vertical side, this one. Okay, and this face is coming from this side. So when these 2 faces are intersecting on this point, that means this point is actually this equivalent point of the cube. So here what symmetry we were having? Here we were having a 3-fold rotational axis. So the 3-fold rotational axis in case of a dodecahedron will be preserved here. Okay, similarly in case of the octahedron, as the octahedron is created by rubbing this corner. Okay, so that means the center of this equilateral triangle is representing this corner. Okay, so clearly the 3-fold rotational axis is preserved on the center of this equilateral triangle. We will see some more objects. Okay, how we created tris octahedron? We added 3 more faces in each and every face of an octahedron. Okay, those faces was created by dividing this equilateral triangle through its medians. So that means the intersection point of the 3 medians will be the point from where the 3-fold rotational axis is going on. Okay, observe here that this is the point where the 3 medians of the equilateral triangle is intersecting. Okay, and this point is representing the 3-fold rotational axis in case of a tris octahedron. Similarly, you can find out the rotational axis or symmetries for the hexactahedron also. In case of hexoctahedron, the original triangular face was this one. Okay, this was the original face for the octahedron. Okay, so each and every corner of the octahedron was denoted by a 4-fold rotational axis. Okay, this is how the symmetries are preserved in case of each and every objects, though they are looking different in apparent view. I guess you have understood now. So now the picture is being cleared. We do not have problem for these 2 crystals, but we had problem for garnet and fluoride. Okay, now see, garnet is crystallizing on a dodecahedron shape. Clearly, dodecahedron can be derived from a cube, so this can belong in cubic crystal system. Again, in case of fluoride, this is actually a octahedron set. Also, octahedron can be derived from a cube, so that's why it is belonging to cubic crystal system again. I think you have found the beauty of crystallography here. This is also a way how can we create octahedron and dodecahedron from a cubic unit cell. Okay, there is no doubt for a cube this can be created from a cubic unit cell, but in case of octahedron we may distribute the cubes like this one and we can create an octahedron or a dodecahedron. Okay, the unit cells are so tiny that the roughness of these faces will not be manifested in case of a resulted crystal. Okay, this will be looked like a smooth face. With that, we have came to the end of the module 1. We have completed 10 classes in the module 1 of crystallography. I think you have enjoyed the session. We will meet again with more interesting topics like this one. Till then, goodbye and best of luck.